Okay, good to see you again. We're on periodic table, the second half of periodic table, so-called thinking questions. We're on the top of page 9, and what I have illustrated here is again a big atom, big nucleus. Remember, the nucleus proportionally is much smaller than the rest of the atom. But just to blow it up so you can get some things. In the nucleus again, the protons and the neutrons. And the number of protons gives us a nuclear charge. So in this case, this atom has 1, 2, 3 protons. We have a nuclear charge of +3 or 3 positives. Nuclear charge is the charge of the nucleus, and it's always positive. The overall atom, if it's neutral, would be 0 because protons and electrons cancel, but the nucleus is positively charged. And then I have here AR, which stands for atomic radius. The atomic radius, you can think of it as the size of an atom. It's the distance from the center of the nucleus to the outermost orbit. So just like in math, you could have 2 circles, one with the greatest radius. The circle with the greatest radius has the greatest size. All right, a little tongue-tied over there. The circle with the greatest size is the one with the largest radius. And then here, we're looking at 2 other properties besides atomic radius, and that is focusing on a valence electron, which is in the last orbit. All right, and last orbit. That valence electron can be subjected to 2 forces, or is subjected to 2 forces. One, the electronegativity, which is the pull of the nucleus, the attraction of the nucleus for that electron. So the pull of the nucleus, because remember, the nucleus is positively charged, and opposites attract. So the electrons are kept in orbit. They don't float away from the atom because they're anchored by the protons in the nucleus. And it's because they're moving that they don't come crashing into the nucleus. Now, since that electron is anchored, then you're going to need energy to pull it off. So that energy is called the ionization energy. That's the energy needed to pull off an electron. The energy I need to pull off an electron from this atom. All right, so once again, these are some key properties, and let's highlight the key words that go with them, and then we'll see how these properties relate to each other in a second. So you'll see these properties also listed in the back, table S. Ionization energy, the IE, energy needed to pull off, the energy I need, not that the atom needs, that I need to pull off an electron. And it's technically the most loosely held electron. So you can have a first ionization energy, a second, a third, but you only have the first ionization energy mentioned there in your periodic table. In your table S. Then the electronegativity, the EN, is the attraction of the nucleus for electrons, or the pull of the nucleus, if you want to play on these words. So the nucleus pulls on the electrons, and the ionization energy is what you need to pull off the electrons. And then again, the atomic radius is the size of an atom. The larger the atomic radius, the larger the size of the atom. And you could look at table S where you have these properties listed, and we're going to play with that in a second. Okay? Now let's continue. You're almost done with periodic table. This part, not much detail to know. Unlike the previous page, when we were on page 8, so many facts. What I have here illustrated is 3 atoms, beginning at the bottom, lower left. I have francium in the lower left, FR. This represents francium. And then I have also, if you go up that group, you'll hit lithium, and I've drawn that as a smaller circle because lithium has a smaller atomic radius. How do I know that? Well, look, lithium is in period 3. Forgive me, period 2. That means it has 2 energy levels, Li. And francium is in period 7. That means it has 7 energy levels. By the way, careful when you read francium there, because you'll notice it says dash 18, 32, 18, 81. And just underneath that, they remind you that they haven't written the 2 and the 8 in because they didn't have space. So the first orbit of francium does not contain 18 electrons. It has 2 and then the second 8. So be careful for that. So francium has 7 energy levels since in period 7, and so it's a very fat atom. And as you go up groups in general, since there's less energy levels, up any group, then the element at the top should be smaller in size and atomic radius than the element at the bottom. And then with that comes the other properties. But before we do that, one more thing. Following atomic radius, if you go to the right in period 2, you'll come across fluorine just before you hit neon. And I've drawn fluorine to be smaller in size than lithium. The question is, why would that be? I mean, they happen to have the same number of energy levels. Well, lithium is atomic number 3. That means it has 3 protons pulling in on its electrons. And fluorine is atomic number 9, which means it has 9 protons pulling in on its electrons. And so effectively, this has a greater pull, and that's what makes it smaller. So going up, the atoms get smaller because there's less orbits. Going to the right, the atoms decrease in atomic radius because there's a greater nuclear charge, and that has to do with protons. All right, so up and to the right, they get smaller. And anytime you take a question like this, the easiest thing to do would be to just draw something like that, very quickly, just to remind you of that, to represent these 3 atoms. Now, how did the atomic radius, how does that play into electronegativity and ionization energy? Well, let's draw the nucleus positive, positive, and positive, and let's draw an electron. Let me just, right now, here, let me just make sure the screen stays on for us. And then, notice that the electron, in the case of francium, focusing on its 1 valence electron in the last orbit, that electron is much further away from the nucleus, the positive, than the electron in the case of lithium, because it's a smaller atom. So that means that since lithium is smaller, it will have a greater hold on its electron. It will have a greater electronegativity, right? Because the attraction between oppositely charged particles is inversely related to the distance between them. What that means, translation, the further away they are from each other, the less the pull of the nucleus on the electron. So francium will have a very small electronegativity. As you go up the group successively, the electronegativity will increase. And as you go to the right, look at fluorine. As illustrated here, the electron is practically on top of the nucleus. So the fluorine will have the greatest electronegativity. And if the electronegativity is so high for fluorine, then the ionization energy, the energy I need to remove an electron for fluorine, will also be the highest. All right, so these things go hand in hand. That means they're directly related. The higher the electronegativity, the greater the ionization energy. Translation, or in other words, the more anchored an electron is, the greater the pull of the nucleus, the more energy I need to pull it off. So think of it as something that goes hand in hand. The greater the electronegativity, the greater the ionization energy. And we could list these properties if you want, or you can just look them up in the numbers, all right, in Table S. All right. In fact, look at Table S. Let's look at the numbers, because you might find this just a little confusing. You know, I'm finding it simple with this diagram, but maybe not for you. All right, so let's look up these properties. Let's look up francium, then lithium, fluorine. We'll look up atomic radius, electronegativity, and ionization energy. So show you that the numbers don't lie. All right, so francium, number 87, has a ionization energy of 393, electronegativity of 0.7, an atomic radius of, it's all the way to the extreme, 270 picometers. I'll avoid the units right now. Then, lithium, all the way up on top, element number 3, has an ionization energy of 520. That's right, ionization energy down here, sorry. Has an electronegativity of 1.0. You notice the electronegativity is getting larger. All right, and the ionization energy is getting larger as the size decreases, because lithium's size, its atomic radius, is 155. So, comparing francium with lithium, lithium has a smaller atomic radius, has a higher electronegativity, and a higher ionization energy. And then let's look up the numbers once you fill those in for fluorine. Fluorine, element number 9, has a atomic radius of 57 picometers, PMs, electronegativity of 4.0, very high, in fact the highest of the nonmetals. And of course, noble gas is another story. And then the ionization energy in this case of fluorine, element number 9, is 1681. And there you have it. Going up and to the right, ionization energy increasing. Because the electronegativity is increasing. Because, ultimately, the size is decreasing. So that's nice with the numbers. You could always look up numbers if you're confused with these relationships. And also, I've summarized it here. Metals in general, the elements towards the left, all right, of the bat line, to the left of the bat line, metals in general have large atomic radii, they're big atoms, and because of that, they have a small attraction for their electrons. That's why they're losers, right? Metals are losers. They lose electrons in chemical reactions. Why? Because their electrons are not as anchored, not as strongly held as the electrons of nonmetals. And they go hand in hand. If the electronegativity is low, so will the ionization energy. Nonmetals, think of them as just being the opposite of metals. So here you have it descriptively, quantitatively, and here's a picture to help you with that. Either way, it will work. The last thing is this thing right here, metallic activity. Francium, as I told you before, is the king of metals. It is the most active metal. It is the metal most likely to do what metals do, which is lose electrons. So it's the one most likely to lose electrons. We can add that too over here. Let's do that. The most active metal is most likely to lose electrons. And as you go further up, they're less likely to lose electrons. They're less active as metals. And to the right, they start becoming more active as nonmetals until we get to the king of nonmetals, which is fluorine, and is the most active nonmetal because it is the one most likely to gain electrons. So, most likely to gain electrons. So metallic activity is a tendency to lose electrons. Non-metallic activity is a tendency to gain electrons. Finally, at the bottom of the table, two more points to make. Then we can look at some questions on periodic table. If you got the energy, otherwise you should take a break. Now let's continue down, and that is the following. Since metals are big atoms, metals lose electrons. They don't hold on to their electrons as tightly compared to nonmetals. So they lose electrons to form positive ions that are smaller in size compared to their atoms. So sodium is our example. Here's a sodium atom. Relatively in size, the sodium ion is smaller. Or by configuration, 2 ain't 1. Remember, the +1 means it lost 1 electron. The ion would be 2-8. You might be saying, well, how could the loss of 1 energy level make it so much smaller? But remember, it's attained now, it has now a noble gas configuration, so it's more stable too. In other words, a fancy way of saying this is, the atomic radius for metals is greater than the ionic radius. The size of the atom is larger than the size of the ion. And for nonmetals, again, it's just the opposite. And finally, the Hankel-Briefs, the 7 Hankel-Briefs, the elements that we always write a 2 after when they're by themselves, because they consist of, samples of these elements consist of molecules that are 2 atoms held to each other. So when we say H2, really H2 is 2 atoms of hydrogen. That would be a hydrogen molecule. 2 hydrogen atoms stuck together sharing electrons. Same for O2, N2, etc. They are diatomic, which means 2 atom elements. All right? So the Hankel-Briefs, or some people remember this as the genenes because they end in gen and ene. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine. Whichever way you want to remember it, or just straight out memorizing. Okay, we're done with periodic table, finally. What I want to do now, and what you should do now, is some questions on periodic table. That will wrap it up. But try doing the questions first on your own. Read through the notes, do some questions. And then the answers are listed for you at the bottom. If there's an issue, either way, you should let me walk you through the explanation. All right, I'll see you then.